Alright, good day everybody, wherever you are. I'm so happy and I'm so excited to be bringing this to you. It's a very big package from CMRC, Creative Mind Real Concept, and I'm most privileged to be the innovator, the initiator of this program. It is a very big success to bring this to you, Free Success Project 2025. And this year, I am so happy. We have amazing facilitators, persons who are selfless, who are passionate, who are explicit in every ramification of their discipline, and they will blow your mind. So I want you to keep your tabs and start watching these videos and get excellent results and come back to tell us, and we'll rejoice with you. God bless you.
Welcome back. Now we are moving to the third subtopic, which is thermal expansion. Okay, let's break it down. What's thermal? Thermal is talking about heat. And then what's expansion? Expansion is talking about when there is increase in a particular dimension of an object. Yeah, it may be length, it may be the breadth, it may be the width. And also when I'm talking about the area, it's talking about the volume. So that means that a particular object can expand in all these dimensions. So now let's move because of our time. Thermal expansion. Now, when something expands without changing its state, that's called thermal expansion. Now, mind you, when something expands and has changed its state, which is state of matter, it is not thermal expansion again. So that's the difference. They can ask in an word statement. If something expands, if a particular solid expands and its state of change has to change, maybe from solid to liquid, maybe from solid to gas, that's sublimation. It is no longer a thermal expansivity. But when it expands without a change of state, it is what? A thermal expansion. So now, let's go to the first part. We have three dimensions of expansion. The first dimension is what? Is the linear expansion. The second kind is the area expansion. And the third part, they call it volumetric expansion. Now, linear expansion is just when a particular object expands in just one dimension. Now, it can be the length. Now, when you eat a marker, you realize that when you eat iron, you realize that maybe at a particular temperature, it would have moved to it would have expanded, like length would have increased. Yes, so that's incremental in length. It's called linear expansion. Okay, what about area? That's what in two dimensions. Maybe it has expanded the length and the radius. So that's when all this ball bearing, yeah, it's inside. I think it's inside new school physics. Ball bearing expansion is just when particular object expand in length and also in the radius, like the diameter, so expand. And the last one is just volume. Volume is three-dimensional expansion, meaning that it expands in length, in length, the the radius and the thickness. So note that. Now, let's talk about something they call the coefficient of expansion. This is just talking about how much an object can expand. It's saying how much an object can expand. So, and the unit is not the unit, do not forget, per Kelvin. Unit is per Kelvin. Or per degree Celsius. But most times they use per Kelvin. So it's always constant for a particular material. Yeah, it may be aluminium. I think aluminium is 2 exponential 10 to the -5 per Kelvin. Yes, that's for aluminium. I think for copper we have copper is 1.6 10 to the -5. So note those are simple ones, because for JAMB can do some kind of bad things, in the sense that they may just give you that thing and they expect you to know all those simple ones. Yes, they apply it those kind of ways. They want you to know some simple ones for copper, for aluminium, for gold, for silver. Yes, because that's why I gave you the bonus earlier, because I want you to know some simple metals that you have to know their expansivity. That's why I structured the subtopics in a way that They will be what? They will be foundational. So now let's go. Now, linear expansion. Now, the formula for linear expansion, the coefficient of linear expansion is represented with what? Alpha. The one for area expansion is represented with beta. And the one for volumetric or volume expansion is represented with gamma. So note all these three things. Now, another bonus on this aspect, a shortcut that is given by I think the shortcut is inside new school physics. The shortcut is gamma is equals to 3 alpha. Beta is equals to 2 alpha. That means that the coefficient of volume expansion equals to 3 that of linear expansion. The coefficient of area expansion equals to 2 that of linear expansion. So, and mind you, JAMB can also they can do a thing in the sense that they want to relate this one and this one together. So that means that you have to know how to do all this kind of algebra. So that means, so it's telling us that even if in a physics exam, you have to be able to very fast. That's why I told you that speed is part of physics, yes, and accuracy. You have to be able to increase your speed and accuracy to a particular level. So that in the sense that they want you to relate beta and gamma together, not even beta and alpha. So that's telling us that, okay, let me just try something. Now let me relate these two together. The alpha equals to 3 gamma, and so you can say alpha equals to what? Gamma over 3. Abina. So now, this one too, beta equals to 2 alpha. So we can say divided by 2 divided by 2. So eventually you can say beta over 2. Yeah. So you can. This is how you relate the. This is how you relate linear expansion to what? To volume expansion, and this is how you relate linear expansion to area expansion. So now let's go to the real calculation. We do one examples in each expansion in each type of expansion. Now starting with linear expansion, alpha, which is the coefficient, equals to L2 minus L1 over L1 T2 minus T1. This is the formula. Okay, the definition of linear expansion is just the change in length per unit temperature change. You see, it's just simple. The change in length divided by the length divided by what? The change in temperature. So if they ask definition for linear expansion, it's just what? It's just the change in the length per unit what? Change in temperature. What about the second one? Okay, let me just say types of expansion here to be fast. Okay, the second one, which is the beta, equals to what? Change in area over unit area over unit temperature. So if they ask what was the definition for the area expansion, is what? It is the fractional change in area over the area times or the per unit what? Change in temperature. And the last one, which is the volumetric expansion, is what? Change in volume per unit volume over what? Over change in temperature. Yes, this is it. So, and also you can have this as sub formula. L2 equals to L1 1 plus what? 1 plus alpha change in theta. L2, the final length, equals to L1, the initial length, 1 plus the coefficient change in temperature. For this one too, you have A2 equals to A1 1 plus what? Beta change in temperature. And the last one, you have V2 equals to what? V1 1 plus beta change in temperature. So you have all these as a what? As a formula. And I advise that you don't cram this, because it is a formula that it has been on my head since like 3 years ago, and I can reproduce it anywhere because I know the formula, which says linear expansion is what? Is the fractional change in length per unit temperature. When you say fractional like that, it means that I've talked about the part that is what? In fraction, or the change in length per unit change in temperature. So now let's try an example to back up my my thesis about this. So what am I saying? I'm saying that let's try question example 1. Okay, which is find the initial length of an aluminium rod that undergo an linear expansion from 40 degree to 80 degree. Now they will give you this, and sometimes they may not give you. Equals to aluminium. Now I told you that it's 2 times 10 to the power minus 5 per Kelvin. So now how do we solve this? I told you that since it is a linear expansion, sometimes they will not give you this, and so the first flag you have to notice the particular this thing. If they say initial length, or when they say the length, or when they say initial area, so you have to know this. It's not the particular metal now, because metal can undergo even an area expansion together with a linear expansion. You can find that out in new school physics. So I'm talking about new school physics because it is the textbook that I touched on part that secondary school physics could not talk, and also the excellent physics, or is it physics, or calculation in physics and essential physics. Thank you. So that's what I'm saying now. So let's go to the solution. So let me give you a tip too. In order to do well in physics, you have to read more than one textbook, because JAMB can do some kind of tricks that they will set the question in the sense that some point will be in the textbook and some point will not be in another textbook. So you have to read up to like 3 textbooks. So what's the formula again? Coefficient of linear expansion equals to the L2 minus L1 over L1 change in theta. So the coefficient is this: 2 times 10 to the power minus 5 equals to, I didn't give us the length, okay, with length, okay, let's say 40 centimeter after expansion. So now let's go. 2 times 10 to the power minus 5 equals to what? The L2, that's after expansion, this 40 centimeter minus what? The initial length, L1. Change in temperature is what? 80 minus 40. So eventually you have to do some kind of calculations. As I told you, and JAMB will not give you a calculator, so you have to know how to solve all these things without calculator. So eventually we get L1 equals to okay, let me bring L1 here. So 40 minus L1 over what? Over 40 times 2 times 10 to the power minus 5. So we get L1 equals to 40 minus L1 over what? So you can say 4 times 10 to the power 1 times 2. So that's 8 times 10 to the power minus 4. 8 times 10 to the power minus 4. So again, I think we still have to cross multiply again. So let's go. Now we have 8 times 10 to the power minus 4 L1 equals to 40 minus L1. So eventually you have 8 times 10 to the power minus 4 L1 equals to plus L1 equals to 40. So eventually you have 1.8 1.00, okay, 1 2 3 4, 1.0008 L1 equals to 40. So divide this. And this you can do it on a calculator. You can do this on a calculator, on JAMB calculator. So now this is a calculation on the on linear expansion. Because of our time, let me take one more for area expansion, or let's say volume expansion too. So now for another example to wrap things up, okay. Now example 2. Okay. Find the initial, okay, let's say find the final area of a let's use copper now, of a copper rod of initial area. Mind you, they may not ask a question like this, but I just want to use it as an example. Okay, of initial area 40 centimeters square, and okay, and 40 centimeters square. Then another thing is that what the temperature change from 40 degree to 80 degree. You may ask me that why is it that I'm not changing the units? The reason why I'm not changing the unit for temperature is because even if you change the unit, it depends on the unit of the linear expansion. It depends on this unit, and if the unit is in per degree Celsius, you have to make sure that you didn't convert. But if it is if it is per Kelvin, you have to convert, because you have to make the temperature to cancel themselves at a particular point in time. So you have to make sure that the unit of the particular temperature is the same with the unit of the degree Celsius. But most times we don't usually convert them to the degree Kelvin. So now let's say we have, okay, hypothetically, let's say 3 times 10 raised to the power minus 5 per degree Celsius. Yes, hypothetically, I don't know, hypothetically. So let's say solution. Okay, now when you see area, that means that it was area expansion. So we can say, now you see that this place I give you alpha. Do not use it with that. Do not use it like this. You have to what? You have to make use of what I gave you, that beta equals to 2 alpha. These are questions that JAMB can give you to give you as bonus question, but you can easily miss them if you are rushing. As I told you, speed and accuracy are very important. So if you use it like this, you eventually miss it. Yes, most times when I'm trying questions, sometimes I do miss this kind of question. But subsequently, when I'm not perfect, I realize that now I can easily do it without even thinking I'm solving question. So it's because I've practiced. So that's why you have to practice more. So now 2 times 3 times 10 raised to the power minus 5. You cannot use it like this. So you have to make sure that it correlates. The area must correlate with with the beta, and eventually you get 6 times 10 raised to the power minus 5 per degree Celsius. Are you with me? So now now beta equals to what? Change in the area over what? Over area T2 minus T1. I'm almost done. This one will not take a very long time. So now beta, what's beta? 6 times 10 raised to the power minus 5. Okay, I think let me try the second formula. Beta equals to 2 alpha equals to 2 times 3 times 10 raised to the power minus 5 equals to 6 times 10 raised to the power minus 5 per degree Celsius. Now let's use the second formula, which is what? Which is A2 equals to what? A1 1 plus beta change in theta. Yes, this formula is also very fast. Okay, now what's A2? The final area, which is what we are finding. A2 equals to what? What's the initial area? 40 centimeter cube. Please always convert your except the unit is also in this kind of unit, in this kind of option. So always convert your unit to the what standard unit, which for length is what? Is meter. So now eventually we do what? 40. Now how do we convert 40 centimeter cube? The fastest formula is just that what? Times 10 raised per what? Times 10 raised per what? Because how many centimeter make a meter is 100. So that's 10 raised per 2. Because it is square. 10 raised per minus 2 because it is square. So eventually you get 40 times 10 raised per what? Times 10 raised per minus 4 meter square. Please, you have to know how to use this kind of scope. How did I solve it? I want to convert centimeter square to meter square. Now, centi and meter. How many centimeter make a meter? Is what? 100. And because I want to convert centimeter to a meter, I have to understand the conversion factor. Yeah, they call it conversion factor. So that's what 10 raised per minus 2. And because the centimeter square, it is not centimeter cube, you have to put the square to balance everything. Eventually you get 40 times 10 per minus 4. Most times, times 10 per minus 4 to just convert. Don't waste your time. So eventually we have to put it here. 40 times 10 per minus 4. 1 plus the beta, which is now 6 times 10 per minus 5. And what eventually you have temperature which is 40. So you get 0.1234, 0.004. Now you have to multiply this one and this one together. So eventually you get 2.4 times 10 per minus 4. And the way I'm solving it is because I have understood the trick, but the trick is just that you have to understand that 40 can be what? 4 times 10 per minus times 10 per 1. So multiply 4 times 6, that's what? 24. But you have to understand that even when you multiply 24, there is still what? Okay, I think it should be 24 times 10 per minus 4. 6 times 4. Let me just teach us this trick. 6 times 10 per minus 5 times 40. This can be 4 times 10 per 1. This is what? 6 times 10 per minus 5. So you can take this and this one together. 6 times 4 is what? 24. Times 10 per minus 5 times 10 per 1. Minus 5 plus 1. That's what? That's minus 4. That's why it is what? 10 per minus 4. So understand how to use all those tricks because it's going to help you in exam. So and eventually you get something like this. 1, 2, 3. You have to be using all these things. They are very important. So you get 0.004. 1 plus what? 0.0024. So eventually you get 0.004 times what? 1.0024. And this can be solved on your what? On your calculator and even we can solve it. Let me solve it. Okay, no, you can solve this in your UTME calculator. So this is a question on area expansion, and this is how you solve it for all those kind of questions. So now let's move to the last part of our discourse on physics, physics tutorial. So this takes us to the last part of thermal expansion, and then we are moving to the last part, which is anomalous expansion of water. Make sure you listen to this part because it does come out, I think, every year, yes, because it's a question that JAMB cannot do without it because it's a practical example. So you have to be there.
Be sure to link up with us, message us, seek out our email, send us messages for further questions and mentorship after you have seen these videos. I'm very happy to say this again, that it's a time for you to move on and succeed. It's a free success project 2025. Bless you everywhere that you are. Again, my name is Emmanuel Aderoju Adeyemo from Creative Minds Concept.